Let's explore what the graphs of radical functions look like. In a minute we'll get to this table with a lot of good interesting stuff. But for now, let's go to our old friend Desmos and take a look and see. Now, some of you might be wondering, what are you going to write as notes? And this is what I'd like you to write as notes. I'd like you to put in f of x, write down f of x equals, and we're going to start off with the square root of x. And I'd like you to see what the graph of square root of x looks like. This is it right here. It's kind of got a classic look to it. So you're going to write f of x equals square root of x, and then you're going to do a quick sketch of what this guy looks like. It does not have to be exact with numbers. You don't have to do grids. Make it easy on yourself. Make it quick. Just do a quick sketch. What's really important is that we have a vertex at 0, 0, and then the line kind of goes up and over to the right, but with a curve, it's not a straight line. And what I really want you to notice is it kind of looks like the line is getting flatter and flatter and flatter over time. Anyways, or less steep, I should say. Now, a few things that I'd like to show you about what happens when we graph radicals like this. By the way, this is the parent graph, y equals square root of x, and this guy. This is the parent graph of all other radical type graphs. So let's take a look and see what I mean by other graphs. Well, first of all, in the past you may recall that we had things where we had other stuff going on in our graphs, like we had a, and then maybe we had x, and then we maybe had minus some number, let's call it h, and then we had plus some number, let's call it k, and I'm going to go ahead and put those guys in there. And it turns out that h and k work just like they did with the other graphs that we've discussed. H is like a hippo. It moves the graph from side to side. Let's try it. See that? Cool, huh? And k is like a kangaroo, and it moves the graph up and down. Okay. And then a did something with the previous functions that we explored. Let me go ahead and put h back to 0 approximately, and we'll put k back to 0. So, and we'll just turn off this red graph for a moment. And then what I'm going to do is I'm going to make a into a negative number. And but before I do, pause the video and see if you can predict what's going to happen to this graph. Okay, are you ready? Here we go. I'm going to make a into a negative number. Drum roll, please. Here we go. Negative. That's it, okay? So if we have a graph that looks like this, if this is our radical function, and we change the number out in front into a negative number, it reflects about the x-axis. So what do you need to write? You need to write this guy down here, and you need to write that h moves the graph from side to side, and that k moves the graph up and down. And if you want to put the corresponding sketch that goes with those, that's fine. The other thing is you're going to say something about a. If a is positive, the graph is above the x-axis. If a is negative, the graph flips down below the x-axis. So this sign, the positive or negative, causes the graph to reflect about the x-axis. Those are the words that I'd like you to write. Okay, you can pause the video until you're ready to keep going. All right, what else are we going to do? I have another video for you. I found another teacher that made a video that talks about vertical stretch and horizontal stretch, and he did a really good job explaining it, so I'm going to let you watch that video to talk about other aspects of A. And it turns out there can be another thing here in front of the X. We'll call it B. And it does things too. But again, I'm going to let another guy discuss that in another video. For now, we're going to focus on A, H, and K. It's going to, so the next thing that I want to do is I want to explore a little bit what the different graphs of other types of radicals look like other than just the square root. We've also talked about nth roots and cube roots. Let's take a look and see y equals. There's a couple of ways to do an nth root in Desmos. You can either go to functions and then miscellaneous, and then down here there's like a square root with a little n. Unfortunately, this square root over here doesn't work very well, so we can do it that way, and I'll show you another way as well. And I'll go ahead and put the third root, and let's go ahead and say x. So now you can kind of see what it looks like when we have these two guys next to each other. You'll notice that the graph of the square root only starts with positive values of x. In other words, the domain of the square root is x must be greater than or equal to 0. But look at the green line. That's what represents the cube root of x. And I want you to notice for the cube root of x can be negative or x can be positive. And that's part of the nature of odd degree radicals. Or odd indexed radicals. Let's take a look at what happens when we have y equals, this time I'm going to type nth root, N-T-H-R-O-O-T, and when I do, I get an nth root, and we're going to try the fourth root of x. And when I do, it looks a lot like the, it looks a bit like what we saw for the square root. Again, x values must be greater than or equal to 0, and that's one of the aspects of having an even index for a radical, is that the domain will always be, well, whatever is inside the radical must be 0 or greater. And just for the heck of it, we'll throw in the fifth root so you can see that. And I would love for you guys to play with this on your own at home so you can get a sense of what happens when you change various things. But again, you can see now that we're back to an odd index, the x values can be positive or negative. And I'll leave it up to you to play around with why is it when we have a negative x value, why is it that we have negative y values as well. I'll give you a big hint as to, again, this is Deepwood's math survival skills. If you ever wanted to know what a strange graph looks like, let's go ahead and put it in writing for you. What do you do if you want to know what a strange graph looks like? It's an easy rule. Deepwood's math survival skills. Make a table. Okay. So in the case of if we wanted to figure out if we have y equals the fifth root of x, what we do is we make a table. X, y, put some values in it, and when we put those values in there, whatever we put in for x, we could try 0, 1, 2, 3, and when we do, you'd have to, on your calculator, raise those guys to the power of 1/5. So like what is 2 to the power of 1 divided by 5? Or if you have the fifth root button on your calculator, you could just use that. And I suggest for this particular problem, for this particular table, you might want to try, since it's an odd root, you might want to try -2, -3, -1, -4, and then see what happens when you take the fifth root. You'll see what the corresponding y values are. And even if you can't sketch them exactly, you can get a sense that when we put in positive values, we get, for x, we get out positive values for y. Put in negative values for x, we get negative values out for y when we have an odd index. Again, you would do the same kind of experiment for if you wanted to test out an even index. And again, you could even use this same idea, make a table, to test out what it looks like when you have something like 2 times the square root of x minus 3 plus 4, and you could change all these numbers, 2, 3, 4, make them fractions. Certainly make this guy a fraction to see what that looks like. Make this guy positive and negative. Try changing these values. Again, like we've looked at in the past, the h, comma k is where the vertex is for radical functions. That's where the vertex is, or the beginning of the radical function. Now, I just included this table in here so you could see it. The table is in your book, and certainly there's tables like this online, but this is a pretty good table that explains what happens to the graph when we change the h value. We get horizontal translation. When we change the k value, we get vertical translation. When we make the sign out in front negative, the graph flips over. And I think what they're saying, what they say is if you put a negative in front of the x inside the radical, then you flip about the y-axis, and if you put the negative sign out in front of the radical, you flip about the x-axis. These are all things that we've seen before. This is not new, but it's worth playing around with to refresh your memory. And again, this sort of stuff will show up on the SAT for this function and for other functions we've seen before, so the review would be worth your time. This talks about horizontal stretch and vertical stretch, and those things will be covered in another video that is part of your homework.